while waiting for the rest to settle down, I kind of have a random question. Today's on hashing, and while I was brushing my teeth, I just had this random poll in my head. Who prefers the McDonald's hash browns over the Burger King hash browns? Who prefers the Burger King hash browns? Okay, no one likes the Burger King hash browns. I want to bet. I have a debate with a friend. He prefers the Burger King hash browns, and I prefer the McDonald's ones. I guess some of you don't even like hash browns. Okay, are we ready to learn some algorithms? Yay! Okay, let's begin. Got a fancy new clicker. Well, it's not new. It's actually kind of old, but it's new to me. Okay, so I've already mentioned this before, but just in case some of you didn't come for Monday class, right? No lecture on, okay, sorry, this part I didn't mention, but I should have. There's no lecture on 3rd of March, in other words, the Monday of week 7, because it's going to be a midterm, right? So it's going to be at 6:30 to 9 p.m. Please be there at this time. Please be there at this time. One-page, two-sided A4 cheat sheet. I think I already mentioned this. Topics up until the Monday lecture, right? So up until trees, okay? I've already uploaded a sample paper. Okay, I didn't have time to put the text on this for the slides, but pay attention to what I'm about to say. The sample paper's mark distribution is not correct. Okay, so if you think to yourself, wow, this question is so difficult, why is it 1 mark? I had no time to balance the mark distribution because I just wanted to show you guys what the questions might look like. Okay, so in case you want to have an idea of what a sample paper might look like, go to Cosmology and try it out. Okay, it's not representative of the difficulty, it's not representative of the mark distribution. It's just an idea of like what questions we might ask you. Okay? Okay, so let's move on. Let's do some fun stuff. Oh, sorry, less fun. Problem set 5 release is going to happen today after the lecture. Okay. Now, why would you want to do this problem set? This is the one that Seth and I kind of like. We have like some AI-related and autocomplete related applications. So if you want to try it out, these are some basic things. In case you thought I was lying to you when I said data structures and algorithms are used for everything, no, I wasn't lying. So this might give you an example of that. We're going to give you half a week of extra time to do the problem set. Okay, so usually I know it's 1 week and I know it's recess week, so it's technically 2 weeks. We're going to give you 2 weeks and a half. Make sense? Okay? Okay, here's the plan for today. We're talking about hashing. Okay, so for the next 3 or 4 days, well, when I say 3 or 4 days, I actually meant like 3 or 4 lectures. We're going to be talking about hashing. Okay, so here are some of the stuff that we want to do. Right? We're going to talk to you about how to use hashing. We're going to talk to you about some of the basic ideas behind hashing. Okay, we're going to talk to you about how to handle collisions, maybe a bit of hashing in Java. Surprisingly, we're going to talk about amortized analysis, which is mostly a 3230 thing, but somehow we're having it now, and a little bit about Bloom filters. That stuff is really cool. Okay, so to get you started on all of these really cool things, right, we should sort of just start by talking about hash tables themselves, right? So today we're talking about hash tables. I guess that's why I asked about hash browns, right? Okay, so do you guys remember what I said about trees? How they were an associative data structure? Right? So remember what that meant was that basically every time you have a dictionary, there's a set of operations, right? And you can imagine how we still have our insert, search, delete, contains, these things are still here, right? But more importantly, right, like I mentioned before about trees, if you still remember what I said on Monday about problem solving of trees, right? The min, max, successor, predecessor operations are things that you get in a dictionary, right? In a symbol table, we kind of say we don't care about those operations, we only want these ones. Right? So take note that when we talk about symbol tables, there is no such thing as successor or predecessor queries. There is no such thing as min or max queries. Right? Why is that? The idea is that now the keys aren't necessarily ordered. Right? So there is no way of comparing to see whether one key is larger. Like, let's say even if there was a way, maybe we don't care about it. We don't care about an ordering. Okay? So then in that case, we're saying, okay, let's forego those operations that we don't care about. We only want to support these operations. And sometimes you'll see problems where we don't care about max, min, successor, or predecessor. Stuff like that. Right? So think of it this way. Here's an intuition. It's not on the slides, but here's an intuition. Perhaps if we wish to support a smaller set of operations, we can be more efficient. Does that make sense? Because if you think about it for a tree, when you wanted to support successor and predecessor and stuff like that, you had to maintain the ordering. Right? That made it possible for you to do max, min, successor, predecessor operations, right? We painstakingly had to sort of maintain a tree, balance it out, have this binary search tree ordering that we had to care about when we did all these things, and that caused a log n cost, right? Think about it this way, maybe if we didn't have to maintain those things and we had a smaller set of operations we had to sort of support, it might mean that we can be a bit more efficient. And that's what you're going to see today. Does that make sense? Right? So, sort of in contrast to what I said on Monday about how if you have problems that need ordering to solve, right? In contrast, you might have problems that don't need that, in which case we can do a bit better. That's the whole point. That's why we're showing you this data structure, this idea as well. Okay, so what is a symbol table? Think of it this way. Again, you still want to map keys and values, right? So let me go back to the previous slide for a bit, right? You still want to map keys to values, right? Thank God for this, so I don't have to jump, right? But you still want to map keys to values, right? So some stuff you can do, for example, you can implement, maybe, for example, you could try to implement a dictionary with it, right? So for example, like an actual dictionary, right? So for example, you can map words to definitions. Over here, maybe let's say we don't care about the successor operation, right? Like what's the next word? Maybe we don't care about that. We just want to map words to definitions, right? Maybe that's one way to go, right? For example, for a phone book, you might just want to map names to phone numbers. You don't care about what's the next name, right? I don't think any of it. Wait, do you guys know what yellow pages are? Are you guys too young for that? Does anyone know what yellow pages are? Oh my God, boomer. Oh my God, you guys, okay, look it up at some point, right? So, okay, anyway, right? So, you look up a name and you want to map it to a phone number because you want to call. No one does that nowadays, I guess, right? So those things you would use a symbol table. Does that make sense? Like for example, for a URL, I don't know if you know this, but when you type www.google.com, how do you get to that web page? How do you know which server you want, right? There's an IP address, right? That's what this means here. When you map that, you don't need to know. You don't care about the successor or predecessor operation, right? You don't care about what's the next URL. Like no such thing. We don't care about that, right? So for these kind of things, you can imagine these as problems, but we don't care about the ordering. We just want to map keys to values. That's it, right? No min, no max here, okay? Okay, so for example, let's say that I tell you right now, I want a symbol table. So I want insert, I want delete, I want lookup, right? And let's say that you know up to today, let's say you haven't learned anything extra yet, right? And we wanted to implement it using an AVL tree. So question, what is the cost of insert and what is the cost of like search? What do we think? What do we think? This is just recap at this point, right? So what is the answer? Which one is it? Okay, log and it's both log, right? Yeah, I see some people raising up their hands and saying for, right? Does that make sense? Right? This is what we've done thus far, right? So here's a contrast, right? We're going to try to do better than this. That's the reason why I brought this up, right? Okay? So, in other words, what I'm saying is that let's try to implement a symbol table so that both the cost of insertion and the cost of searching it is fast. It's O1. That'd be great, right? That's magical, right? And again, the intuition I want you to have is that because we don't care about orderings, we can try to do this, okay? Okay, so one other thing you might ask is the difference between a dictionary and a symbol table, right? So if you're trying to, let's try something, right? Let's try sorting with the dictionary, right? So like when I say dictionary here, think of this as like an AVL tree, right? What we can try to do, one way of sorting, instead of quicksort or merge sort, we can just use a tree, right? Just very simply insert all of the items into the tree, right? Look for the minimum item, output it, remove it, find find the successor or whatever along those lines, right? So if let's say that we just use an AVL tree, right, to implement this sorting, right? What is the running time? N log n, right? Because the cost of you're inserting n items, each of them costs log n time to insert. Make sense, right? Does that clear? Make sense, right? Okay. What about with a symbol table? What do we think? Is it ON? That would be magical, right? I already said that the cost of insert is O1. So what are we missing? Is it ON? Sorry, construct what? Okay, so I would argue constructing the table is still ON, right? There's a bit of a caveat here, right? For me, like what operation is missing from the symbol table? What operation is missing? For me to output everything in a sorted order, I need to output the value and then find the next value to output, right? The successor operation, right? And like I mentioned, a symbol table doesn't provide that, right? So because of that, it actually costs n squared, right? If you think about it, the only way for you to do it is to pretty much just go through the entire symbol table again to find what the next value is yourself, right? Does that make sense? So you wouldn't want to try to solve ordering problems with a symbol table. That's completely not the point, right? Okay, so again, one thing you might want to think about, this is a bit of an aside. It's a bit more of a sneak peek into C230, right? But you might ask yourself, like, is it impossible? Is it possible at all? Here's the idea. You're gonna at some point realize that sorting actually takes n log n comparisons. You can actually prove this. It's very cool. If you want to know more, come to the forums and ask me. Right? I can show it to you. Okay. So how do you sort with a symbol table? The idea is that you only have these operations. These are the ones that we support. Right? So you kind of have to find, like, you kind of have to go through the entire table. That's the idea. Right? And if you wanted to use binary search, for example, that also needs a minimum amount of comparisons. This is a bit of an aside. I don't want to spend too much time on this. Okay. But the idea here is the following. Here's an observation you might make, right? That if I want to do like insert and search, stuff like that, right? If I want to do this in O1 steps, right? We kind of need to do stuff that is not comparison-based. This is a takeaway I want you guys to know about, right? When you did your quick sort, when you did your merge sort, when you did your insertion sort, your selection sort, your bubble sort, anything, you always have to make a comparison, right? And then from that comparison, you decided what to do. With a binary search tree, it's the same thing. You make a comparison when you decide where it inserts, right? So from this point onwards, we're going to depart away from making comparisons and not do that. We want to avoid this because this is a bottleneck. That's the idea. Okay? Okay, so let's try building a symbol table. So here's an idea, right? Let's say for now, hypothetically speaking, I have a table of size 10, right? It starts from 0, so it's 10, right? Okay, I have a table of size 10, and let's say that I basically want to store some items, right? So here are my keys and here are my values, right? So I have key, for example, 2, 8, and 5, and I want to associate it with items 1, 2, and 3. Okay. Again, we're going to say that we're going to assume that the keys are distinct. This is your sort of like unique identifying thing, right? And I want to somehow insert it into a table. And here's the idea, right? If I knew that my keys were definitely of like some values, let's say that I knew that my keys were always between the range 0 and 9, right? A very easy way to make a symbol table is to pretty much just make a table of that size, right? If I know that my key values were 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, why not just make a table from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9? Right? Then when I want to store an item, all I have to do is go into that index and place the item there. Make sense? Right? So if I want to find it, again, I just use the key value, go to the location, right? So this is basically an array list. Okay? So here's a possible attempt, right? And it's a nice thing to do. If you know for a fact that your problem has this nice structure, right? Then that's probably the best approach, right? This is O1 for lookup and O1 for insert, O1 for delete. We agree? Make sense? Okay? So for example, let's say that we want to insert like Seth as key 4. What we could do is just go to the 4th location and place Seth there, right? So now this one is O1 insert, O1 search. It's also O1 delete. You can go there and remove Seth if you wanted to in O1 time. Okay? So that's nice and all, but we want to solve a lot of different problems, and it's going to be the case that not all the keys are integers, right? So for example, what if we wanted to store strings? Right? What if I wanted to store I was going to say transcendental number, but maybe that's too mathematical of a term, like an irrational number, right? Something that has like an infinitely large precision. How do we do this? Right? That's really tricky. Okay? So apparently, what we're going to try to do is just turn everything into a number. We're really going to just try to turn everything into a number. Okay? So here's sort of the rough philosophy I want you guys to think of, right? If it's possible, I mean, it definitely is possible. That's usually not the issue. The issue is how to do it efficiently, right? But basically, we want to sort of try to convert everything to a number. So here's an example. If I have 26 letters in the English language, right? I only need 5 bits to represent a letter. Do we know how I'm doing this? The first point. Do we know how I'm doing this? So 2 to the power of 5 is 32, right? So if I want to represent 26 numbers, I need to find the smallest of power of 2 that's larger than 26, which happens to be 32. That's 5 bits, right? So if you guys don't know this yet, look up what's called an ASCII table. They basically do that. Every letter has a number that represents this. I kind of wish they taught you this in ONS. I don't know why they didn't. I really, really wish they did. Okay. I don't know, maybe they're wishful thinking it away, like, it's kind of sad. Okay, anyway, moving on, let's not get sidetracked here, right? So, for example, let's say that, this might be the longest possible word you'll ever see in the English language, right? So here's an idea. If this is the longest word you want, and we want to sort of store possible words, right? Here's what we could do. We could say that basically, the most number of bits we ever need is 140 bits for a single word, okay? And I want to insert any possible word in the English dictionary, okay? So what we could do is just force it by making an array of size 2 to the power of 140. Okay, what am I doing here? Why is there a 2 to the power of 140? Here's the idea, okay? I'm going to have a 140-bit long array, okay? Oh, sorry, this is wrong. This should be 2 to the power of 140, okay? And the ith position is for the ith word, okay? So if the ith bit is 1, we know the ith word is being stored. That's the idea. By the way, don't do this, right? Here, let me, I know I just said this. I know some of you are going to take notes thinking, okay, this is how we do it. Don't do it this way, please, okay? This is larger than the number of atoms in the observable universe. So I don't know how you're going to accomplish this. You can't just download more RAM, right? Not possible. I'm just saying that hypothetically you can, right? But just because you can doesn't mean you should, right? Okay? The point of this was to tell you that there are smarter ways we should go about doing things, right? And it's not just should, but we definitely do. Okay, so let's think about this. Okay, so another issue is the following. Let's say forget about strings. We had a size limit on that, right? But what if we wanted to represent something like infinitely long, like decimal, like irrational numbers? What if we wanted to represent just any possible integer, right? Then how do we even do this? How do we even encode this as a number? That's tricky. Right? So right off the bat, this is a losing battle. This is literally downhill. Like it's 16 minutes in and we're fighting a losing battle, right? So here's an idea. We kind of have to make a few assumptions. And here's what I'm going to do. I'm going to say that while it is true that the set of possible keys is very large, the number of keys that I actually wish to store is very small. Okay? So let's say that we want to encode integers. It is true that even for Java, let's say 2 to the power of 64, that's around, let's see, even if I don't, okay, let's see, 2 to the power of 64 I think should be around 2 to the power of 32 is 4 gigabytes, so 2 to the power of 64 is some insanely large number, right? 4 gigabytes might sound cheap to you, but I don't really want a table of that size, right? So instead of having a large table that encodes all the possible keys, here's an idea. Maybe I say in practice, but let's just think of it this way, right? Let's just assume that the number of keys that we wish to store is actually really small. Okay, so while the gray universe is where we have like all these possible values we wish to encode, right? Let's say that we know for a fact that we're not going to store at more than like n of them, right? So the size of the keys that we wish to store is actually really, really small. Okay, so the idea is that we basically only want to map the keys that we care about into m buckets, and think of the buckets here as the size of the table, right? So if I have 5 buckets, think of this as a table of size 5 for now. Does that make sense? Okay, so the question is, how do we do this efficiently? Okay, so let's get to it. The idea is that we're going to try to do a random mapping. Now, at this point, some of you are probably thinking, okay, random mapping, like perfect, right? This is a bit intricate, so I will say a few things about this. It's a bit intricate. For now, think of this as intuitively random. It's very paradoxical. I'll try to fix it before the end of the lecture, right? But think of it this way. So I'm going to create what's called a hash function. I'm pretty sure some of you have heard of this before, and it's a very overloaded term in computer science. But if I had a penny for every time we all named everything consistently, I'd be so rich I don't have to work, right? So here's the idea. Here's a hash function, and think of it this way. It's a function that maps from the universe to one of m possible values. Okay? So why one of m possible values? Here's the intuition. When you use the hash function, it's going to tell you which bucket to put that item into. Does that make sense? Right? So this function has to be evaluated on any possible input, but it has to give you one of m possible values. Okay? And the idea is the following. Let's say that I want to store key k. I will evaluate hash function h. That gets me a value. I will store it in the corresponding bucket, h of k. So if, for example, let's say k is 5, and I hash 5, and it gives me 6. That means I'm going to go to bucket 6 and place it down there. Good? Make sense? Okay? So what is the time complexity? Right? Usually this would be the time to compute the hash function. If you have a really expensive hash function, I'm sorry, that means it's going to take forever. Right? Typically, we want this to be cheap. So we will try to consider options that are cheap. Okay? And the time it takes to access the bucket. So if I pretend that this was a random access array, like an array list, the time to access the bucket would be 01. Does that make sense? Right? Okay. So usually we want to assume that the hash function is cheap. It's cost 01. That's perfect for us because that's our goal. We want our insertions to cost 01 time. Okay, unless otherwise specified. So imagine if you're hashing a very long string. If your string is length L, right, and you have to run through the entire string to compute the hash function, I'm sorry, then it takes OL time. That's a bit unavoidable, right? Okay, but some stuff to consider. Okay, so here's what I want you to think of. Here's the part where I say it's a bit paradoxical. So I'm going to try to say it a little bit slowly, okay, but here's the idea. We're going to think of a hash function as a function that we randomly create before any insertions. So you want to randomly pick values for your hash function before you do any insertions. Okay? Then all insertions look up and deletes when you use the same hash function. Right? So you wouldn't go, oh, today I'm feeling like the hash function should look like this. You insert some values, and then the next day you're like, you know what, I changed my mind. This is a better hash function. We're not going to do that. Right? You randomly pick the hash function once and for all. Okay? here's the idea. For example, if I want to hash numbers, right, maybe what I do is I pick a random prime p as an example and a value a, and then this is my hash function. I do it once, only once. Okay? All insertions, deletes, lookups now have to use this hash function. Okay? This way, you sort of have this nice thing where the same key always has the same hash, right? But it's random. Does that make sense? It's a bit paradoxical, I know. Try to get used to this concept, right? Okay. I preempted myself again, damn it, right? So again, if our keys to be inserted don't know what the values p and a are, right, they'll be hashed to a random value from their perspective. That's the idea. But if you're given the same key, we're always going to hash to the same value. Okay? So here's an idea. Let's say that I have a bunch of keys, right, and I want to hash it to my initially empty table. Maybe let's say, for example, I hash k1 and it maps to 2. So okay, I go to the second bucket, I place my item there, right? And then maybe let's say I want to hash k2, and that hashes to 8, so I go to the bucket there and insert that, right? So on and so forth. But there's a chance that things are going to collide, right? We don't know in advance whether our hash function is going to prevent this, okay? And you might think to yourself, how do I handle this, right? This is a very common issue. Okay, so we're going to say that two keys collide. This is an actual term we use, collide. Okay, if the two keys are distinct, in other words, k1 is not equal to k2, okay, but the resulting hash value is the same. That's called a collision. Okay, so here's the question: can we choose a hash function that has no collisions? What do we think about this? That'd be great, right? If we had no collisions, we don't have to handle this. Everything goes into the table in the perfect location, right? So what do we think about this? Who thinks it's possible to pick a what we call perfect hash function? Who thinks it is? Who thinks we have to be very careful about it, but it can be done? Like, you know, that's kind of funny, right? There's a yes and a sometimes. Who thinks it's impossible? Okay, interesting. Why do we think it's impossible? What's the idea? There's a very, very nice three-letter way to say what you want to say. PHP, right? Something hypertext protocol. No, I'm kidding. It's pigeonhole principle, right? Okay, so here's the idea. If I have a lot of keys, if I have like my universe is insanely large, right, 2 to the power of 64 or something, and my table is only size 5, right? You can think about it this way, right? Because the universe is so large and my table is going to be really small, that's what we want, right, to be space efficient. Okay, the pigeonhole principle pretty much says that you're going to map two keys to the same bucket, right? So collisions are unavoidable. Okay, unfortunately, sad fact of life, right? Like, you know, we have to make do. Okay, so we have to cope with collision. Wasn't me who used this term, but I thought it was really funny because when I was looking at the slides, I was like, copium. Anyway, okay, so here's an idea, right? We want to sort of deal with collision somehow. There's many ways to do it. One way is to choose a better hash function, right? You might think to yourself, by the way, this sometimes works. This is more of an engineering thing rather than a CS math thing, right? You might want to look at the nature of your data and say, okay, I know that it always works this way, so I will pick this hash function. So collisions are very rare, or maybe they don't even happen, right? Another way to do it is that let's say you insert some values, and then you realize there's a collision. You can try to pick a new hash function after that, right? But the problem with this is that you have to recopy the entire table, right? And eventually there's going to be another collision. Okay? The reason why we have to recopy the table is, again, like I mentioned, if you change the hash function without rehashing the elements, you won't know how, if you use the previous hash function to place the items and you suddenly change the hash function, all of a sudden you don't know how the items got there in the first place. You can't find it again, right? The hash function is really telling you where to go. That's the idea. Okay? So these kind of approaches, we might want to discard this. We want to think of something else, right? So here's an idea. Instead of trying to avoid collisions completely, right, let's pretty much just try to deal with them directly. Okay, so for today, I'm going to show you a sketch of how to do this with chaining, right? And then next time around, we'll talk about open addressing. Now, random aside, but open addressing is super fun. The math behind it is really, really cool. It's it's some of my favorite math. Okay, anyway, that was the random aside. Don't get me sidetracked. I'm not going to start showing you a bunch of math, right? Okay, so here's an idea with chaining. So I mentioned that there were going to be a bunch of buckets, right? So on the slides right now, I have 10 buckets. Okay, here's an idea. Okay, instead of just storing the item at the bucket itself, why not the bucket itself stores a linked list? Okay, so what we're going to do is the following. In this table right now, A, C, and J, let's think they're keys, right? We hash them, and they hash to the same location. Okay, so how do they share this bucket? Well, let's just have a linked list that kind of stores all of these items together. That's the idea, right? So every time I want to look for H of A, every time I want to look for A, I evaluate H of A, I go to this bucket, I find it in the linked list. Turns out it's there, that's fine, right? If I want to look for C, I hash it to this location, I find that the first item of my linked list is A, that's not the item I want, but the linked list is not done, so we keep going, right? Then we find that it's C. Does that make sense? Right? Okay. So based on this, what's the total space usage? Well, we needed space to make this table, so that's M, and as well as the number of items that we're storing, that's N. So what's the total space that we're using here? What do we think? Deep down, everyone's thinking, oh no, there's two variables now. How do I do this? I've only seen single variable functions. Okay, so here's the idea. The total space is M plus N. Does that make sense? Right? You needed space for the table. You needed space for this bucket, this table of buckets, and you needed space for the items themselves. So that's M plus N. Okay? Make sense? Okay, so that's one thing to take note of. Now let's think about how these operations work, right? So if I want to insert into the table, all I have to do is calculate the hash function, look up this bucket using the hash function, and insert this into the linked list. Okay? Pay attention to how I have to insert both the key and the value. Okay? So some of you have asked me before in the past, why is it that we have to insert both the key and the value? Here's the idea. If you landed in this portion of the bucket, all I know is what you hash to. I don't know the actual key value itself. Does that make sense? You could have had multiple keys that hash to the same value, right? So the key is the uniquely identifying factor of the item. So you have to store the key along with the value in the list, right? Okay. Now to search, like I mentioned before, all you have to do is again calculate this hash function and then look for this key value pair in the linked list. Does that make sense? Right? Assuming that the hash function on the same key always provides the same value, you will always go to the same linked list and you will always try to find it there. You can be rest assured the key is not in any other linked list. Okay? Okay, so what is the worst case cost of inserting a key value pair? Worst case. What do we think? Let's say that computing the hash function costs O1 time. Or actually, no, hold on. They put cost h here, so I guess that's just, yeah. It's not a trigonometric function, yeah? That's the cost of computing the hash function. So what do we think? Is it n? Is it 1? Is it log n? Is it n squared? I feel like this is the funniest, right? Because it doesn't even have like cost h in it. Right? So the idea is that we're going to say that it costs O1 plus cost h, right? So here's the, okay, wait, hold on. Ignore this duplicates thing, right? Why is it not n plus cost h? That's an interesting question, no? Why is it not O1 plus cos h? Do I have it in the next slide so I don't preempt myself? No, I don't. Why does the insert cost O1? We have a length of a chain, right? So why is it O1? What can we do? It's a minor speed up, but what can we do? So here's an idea, right? Instead of trying to traverse the entire linked list and place the item at the end, let's say I want to hash a new item and it hashes to this bucket, right? Instead of inserting it all the way at the end, why not insert it as the new head? Hey, that's O1. So it doesn't even matter how many items are in your linked list. That's crazy, right? Okay, I'm the only one who's amazed by that. Damn it. Right? Okay. Yeah, okay, hold on. If we care about duplicates, yes, it costs a bit higher because you have to store duplicate keys. You have to figure out which one is the one that you want, stuff like that, right? But yeah, that's an assumption that you have to make. Okay, so lookup and insert are going to be O1 because you're going to append to the front of the list, right? So what about search? So we've talked about inserting and we talked about lookup, right? Sorry, we've talked about insert. What about lookup? What is the cost now? What is the cost now? What do we think? Is it still O1? Why not? Because you've got to go through the entire list, right? Does that make sense? Right? Inserting was cheap because you could just say, I don't care what the list has, I just have to dump it in, right? And insert it as my new list head. But when you try to look for an item, it could be the case that in the worst case, the item you're looking for is all the way at the end of the list. Right? And if you're super unlucky, all of the keys map to the same bucket. So again, sorry, we've created a very fancy linked list. Right? You have to sort of traverse all the way to the end in the worst case. Right? So it's a bit asymmetric. I know the OCD amongst you might not be very happy with this. Okay? But we have a fix, right? Because I promised you today we're doing O1. Right? So this O1 has to go away somehow. Okay? So just bear in mind that we want to focus on these two operations for today, okay? And bear in mind here that the time it takes for you to search, the running time for you to search on a table, a simple table, depends right now on the length of the linked list, okay? It's true that in the worst case, it's on. We're going to try to show you that basically this almost never happens. That's the idea, right? Okay, so how do we do this, right? So again, just so that we're clear, in case you spaced out for the last like 30 seconds, right? How do we get the worst case? In the worst case, let's say that all of the items hash in the same bucket. So again, you just have a very fancy linked list. This list is of length n, and your search runtime in the worst case is going to be on. It's even worse if the item doesn't exist, because you have to traverse the entire linked list. We agree? Does that make sense? Right? Okay, so we're going to use something called a simple uniform hashing assumption. Back in the old days, your seniors would call this SUHA for some reason. Okay. Now, I want to be very clear about this. It's an assumption. Okay. When you move on to higher level in algorithms, we try to remove this assumption by giving you actual hash functions, right? But for now, the problem is that you don't have enough of a math background for me to actually push through like very complicated hash functions to you. Okay. So my point is this is a simplifying assumption. It makes things easy for us to do what we want, which today means caring about how to handle collisions, right? This way, we don't have to talk like until the cows come home about like new hash functions and stuff like that, right? Okay, so these are simplifying assumptions. I don't want you thinking after you graduate that basically all hash functions behave this way. We still have to take care in creating our hash functions, but we're going to say, assuming that someone did that work for us, we get to enjoy these very nice properties. Okay, so what does the assumption state? The assumption states two things. It states that every key is equally likely to map to every bucket. Okay, that's assumption one. Assumption two is that keys are mapped independently. What does independent here mean? It means that if I know where key 1 is going to, it doesn't tell me any information about where key 2 is going to. Does that make sense? Okay, so in other words, think of it this way, the outcomes of the keys are not correlated. After you take SE2040, what I say here is going to make sense, right? Okay, so here's an intuition. Again, I know random here, like we're really abusing this term, right? So again, the intuition here is that you can think of SUHA as basically saying that every key is equally likely to end up in any bucket, right? And then as long as we have enough buckets, we won't get too many keys in one bucket, right? So it's true that in the worst case, it will still be on cost, but we're gonna say that on average, in expectation, right, that's not the case. We're going to use SUHA to prove this, right? So very importantly, I still want you to remember this. The hash function always returns the same value on the same input. This is true, right? Some of you might be confused about this wording, which is why I had to add this note in, right? Like the hash function is fixed. When I give it one key, it will always give me the same value. It always gives me the same value. It doesn't change its mind the next day and say here's a new hash value. No such thing. Okay? Okay. So here's a question you might ask yourself. Why are we using hash functions? Why not, when you give me an item, I just randomly place each key into a random bucket, right? So you give me a key, I look at it, and I tell myself, you know what? I'm feeling a little, like 5 today, so go to bucket 5. Why can't we do this? What's the issue with this? Why am I mucking about hash functions? Sorry? What do we think? So this is the dead horse I keep beating, right? And I keep saying it because students all over the years always get very confused, right? But of all of these options, I don't know why that actually took time to appear, but like of all of these options, right? Let's not go through all of them, I don't have much time, right? The idea is that the searching is going to be very slow. What do I mean by this? This, in my opinion, is not very descriptive, right? Here's the intuition. The hash function tells you where the key is, like where you should look for the key. Right? It basically is random but consistent, right? I know, paradoxical, right? To tell you where to look for the key. So if you want to search for the key again, you have to use the hash function again because it always gives the same answer to the same key. That's the idea, right? If we just randomly threw keys into buckets, we don't know where we put it, right? Imagine if I inserted 5 and instead of using a hash function, I said, okay, you're inserting 5, let's put you in, like index 21. The next time around, I come to you and I say, I want to look for key 5, right? You might look at it and say like, you know what, I'm feeling like index 0 today. You're not going to find the item. Does that make sense? Right? Okay, this is the dead horse I'll stop beating. Let's move on to analysis. So we're going to make the simple uniform hashing assumption. Okay, you know what, it's a mouthful. I'm going to call it SUHA as well. I'm your senior, I'm going to call it SUHA. Okay? We're going to use SUHA. Okay? I'm going to assume that we have n items that we wish to insert and we have n buckets. Okay? I have n items I wish to insert, and my table is of size m. Okay? So a load factor of a hash table is going to be n over m. Here's the intuition. Think of this as the average number of items per bucket. Right? So if I had 10 items and my table is of size 5, my load factor is 2. Does that make sense? Right? If I have 100 items but my table is of size 600, then my load factor is 1 over 6. Right? Think of this as the average size of each bucket. Right? This is what we want to accomplish. Okay? What I want to show is that the expected running time, we're back to randomized analysis, right? The expected running time, okay, is going to be, let's say O1, sorry, I didn't have space. I put an O and it shifted everything down, so you're going to have to live with this. O1 plus the expected number of items per bucket. Right? Does that make sense? The expected running time for search, right? Because for me to search, remember, in the worst case, I have to run through the entire linked list. So if I prove to you that the expected size of the linked list is small, then we're good. Right? Okay? We want to show that this is small, this is constant. That's what we want to show. Using Suha, we're going to show this. Okay? So, again, with probability theory, I'm going to skip this part because we already talked about it. Also, I already mentioned this part again, so I'm not going to talk about it. But TLDR, in a single line, E of A plus B is E of A plus E of B. Okay? So, for example, if I have a random variable who's, I have two random variables, and each of them have expectation 1 individually, then to add them up, I just add up their individual expectations. We've mentioned this before. I'm not going to do it again. Okay? Okay, so here's the idea. Okay? I want to count how many items in expectation land in a bucket. So how do I do this? I'm going to use a random variable. Let's call it xij. Think of this as a random variable that only takes 2 possible values. It either takes 1 or it takes 0. It takes 1 if item I is going to be hashed into bucket j. Okay? So, the simple uniform hashing assumption says that every key is equally likely to map to every bucket. This is what we're going to use. Okay? So, what is the probability that item I maps to bucket j, is hashed to bucket j? There are n possible buckets. So what should the probability be? Is it 1 over n or 1 over m? I hope you, okay, I can't tell because all I heard is the part and not the or the part, but I hope you guys know that it should be 1 over m, right? Because that's that many buckets. Okay? Okay, so the probability that xij is 1 is 1 over m. That's literally what's written out here, right? That's the math. Okay? So I have the probability. What is the expected value of xij? Well, by definition, this happens to be 1 times the probability that xij is 1 plus 0 times the probability xij is 0. Okay? Now, last I checked, 0 multiplied by any value is 0. And 1 multiplied by any value is the value itself. So the expected value of xij happens to be 1 over m. I did a rug pull, didn't I? I told you we'll be learning algorithms, but instead we're doing math here, right? Okay, so how is this useful? Why do I care about expectations, right? I care about expectations because I want to ask myself, what is the expected number of items in the bucket, right? So how do I do this, right? This is the question I wish to ask. It happens to be stated in English. Let's do it in math, right? So here's the idea. If I have xij, I could sum across all of the possible i's, all of the possible items I wish to hash. Okay, and I fix b. So what is this? This summation is basically the number of items that land in bucket b. Okay, so here's the intuition. If I sum across all the possible items, the items that hash to bucket b add 1 to this summation. The ones that don't hash to bucket b add 0 to the summation. Right? So this literally counts what I want. Does that make sense? Okay? Okay, so here's the idea. Think about it this way. If I want to count the number of items that hash to bucket 2, right, this x of, let's say, a2, x of c2, and x of j2 will add 1 to the sum, whereas x of b2 will add 0 to the sum. Right? So the random variable literally evaluates to value 3. Okay? So I want to calculate this. Right? This is exactly what I had just now. It happens to be the expected number of items for the bucket. Okay? So let's work it out, right? By linearity of expectation, E of the summation of random variables is the summation of E of the random variables. Oh no, like a lot of symbols, a lot of letters, right? But look, in simple terms, take the E, put it on the inside, right? Easy clap. Okay, so what do we do after that? Well, I know how to compute the expected values of the individual variables, right? We did that just now. That happens to be 1 over m. Okay, how many times am I summing 1 over m to itself? N times, because there were n items, right? So this has to be multiplied by n, which gives me n over m. Wow, I love this thing. Like now I don't have to jump anymore. My knees will thank me, right? Does that make sense? This is the math. Okay? So what have we done? We've shown that if you have n items that you wish to hash, assuming simple uniform hashing assumption. Okay, assuming Suha, right, with a table of size m and n items, the expected size of the linked list is n over m. The expected size, the average size, the expected size. Okay? Okay, so what does that mean, right? What does that mean? That means that my expected search time is going to be O1 for my hash function, right, plus the array access into the table, right, plus n over m. That's my expected size of the list. Okay? That's the expected size of the list. So, question. Now that we have this, what should I set m to be so that this is O1? I know I have n items. What should I set the size of the table to be? Anything along the lines of n, right? You could set it to be n, you could set it to be 2n, you could set it to be 5n, you could set it to be half n, it's completely fine, right? For example, if you set it to be this, right? Anything that is a constant factor multiplied by n, at least a constant factor multiplied by n, right? Then we know for a fact, for example, m is equal to 2n, we know that the expected running time for search is going to be O1, right? This is not the worst case, right? This is the average case. Does that make sense? Right? Sorry, the expected running time. Good? Okay? Okay, so that's the idea. Okay, so just to recap a little bit right now, right? The expected search time happens to be O1. Again, if you're super unlucky, you could have still picked a hash function where somehow, the world hates you, you didn't, you won the lottery in the opposite way, where somehow, like, after you lose, when you lose it, they take $1 million away from you or something, right? Literally, it could still be the case. There is still a small chance that, like, everything hashes to the same bucket. That might happen. So the worst case time is still ON. Okay? Sorry, this can't be avoided, right? This can't be avoided. Okay? Insertion, if you do it cleverly enough, this is O1. Okay? So why do we use hash tables? Here's an idea, right? Maybe we should not all be as pessimistic, as we should be. And sometimes, if we're happy enough with expected running times, we should just, be happy to use this data structure, because maybe, like, for the most part, it will work out and it will just be O1 insert, right? It depends, right? So if you have an application where you definitely don't want to pay the cost of, like a unlikely worst case, maybe it's like a very mission critical thing, right? Maybe don't use a hash table. Maybe you're happy to use one because, on average, if it works out, it's good, right? Then maybe use a hash table. Does that make sense? Right? I can't like sort of like hit on this point enough, right? You have two possible points of consideration here, right? If you're okay to risk a little bit of worst case running time, right? It might be fine to just enjoy the benefits of expected running time, like the expected low cost of running time. It really depends on what your application is. Right? But I really want you to remember both these points. Okay? Okay, I already preempted myself like so many slides in advance this time. Why not ON? I already told you, inserted the head of the list, right? Okay, so one more thing that you might want to ask, okay, this is a bit of a cool question. Okay, sorry, I know when I say cool, people are going to be like, cool? Is it really cool? Anyway, a bit of a cool question in my opinion. What happens if I want to insert n items into my hash table? What is the expected maximum cost? Okay, how do we even define this is a bit tricky. Here's the idea. This question is asking something different. The question before this was asking what is the expected length of the linked list. This is saying that after we hash the n items, go through all of the linked lists, find the maximum one, and report the maximum length. Right? What is that length? Okay, so here's an analogy. Okay, when I say this balls and bins thing, it's actually really famous. So if you ever start studying theoretical CS like I do, this is a very, very common math and stats problem, or CS problem as well nowadays, right? The idea is that under Suha, you'll be throwing n balls into n bins, right? What is the maximum number of balls in a bin? That's the idea, okay? You can prove that it costs log n. This is not too hard to do. I challenge you to try doing it. If you're really careful, you can show that it's log n over log n. So somehow, some genius saw this and thought to himself, this is not good enough, and decided to prove this. Okay? You can come to CS2040 for a proof of this. I took this mod when I was a second-year student, so you can imagine my mind was really blown. It was really cool. Okay? Again, this is beyond the syllabus. We're not going to expect you to know this. Okay? The intuition is the following. Okay? Why is this important to know? here's the idea. This is a way of sort of arguing that your worst case running time is not too bad. That's it. That's the only takeaway I want you to take from this, right? It's also a very fun math puzzle. So if you want to try to solve it, you don't know how to start, come to Cosmology, pose the question and say, hey, Eldon, I want to try solving this. Walk me through it, right? I'll do that for you guys. Okay? Okay, so let me do a quick recap. Okay? So, again, a few things I want you to take note of. Okay? Usually when we hash things, the number of possible keys is very large. We don't want a table that can accommodate for all of them, because likely we won't be storing all of them anyway. Okay? So using something like a direct access table, in other words, a table that literally potentially stores all of the items, is literally way too much space. We don't want this. Okay? Hash functions are nice because they basically consistently map the same key to the keys to the buckets. Call it with the same key, it will always give you the same bucket. Okay? Sometimes keys will collide. We cannot avoid this because of pigeonhole principle. Okay? So for today, not tomorrow, not the day after, for today, we are using a linked list to sort of deal with collisions. This is the easiest solution. And fun fact, for those of you who want to know, C++'s implementation does do this. So it's not just of theoretical interest, they actually do this. Okay? It comes with implications. So there are reasons why you don't want to use C++'s default hash table, because it comes with these kind of performance implications, right? But for us, because we want to push you through the math, what we did today was sort of show you that the expected number of keys is 01. Again, very important. I cannot stress this enough, right? The worst case is still 01. The expected is 01. There's a difference. Okay? It's not splitting hairs. There's a world of a difference. Okay? Yeah, simple tables are pervasive. I've already sold you on that, right? Yes. Okay. So I'm not going to say too much about this. So yeah. Okay. One more thing. So to contrast this against your binary search trees, right? We're not doing comparisons anymore. We're operating directly on the keys themselves, and we gave up successor, predecessor, min, and max operations. Okay. So with that, I end my time. Good luck for your midterms on Monday.